Hello everyone, my name's Iman. Welcome back to my YouTube channel. Today we're going to be covering Chapter 12 for our MCAT Physics and Math playlist. And this chapter is titled Database and Statistical Reasoning. This is our last and final chapter for this playlist. With that being said, I want to take a moment to tell you how proud I am of you. Being pre-med is not an easy path, but here you are, finishing this playlist and accomplishing one more step on your journey. So I want you to keep pushing forward and remember, never let short-term discomfort compromise your long-term goals. So with that, let's go ahead and cover what objectives will be taught in this lecture. The first objective is titled Measures of Central Tendency. So here we're going to discuss mean, median, and mode. And these measures help us summarize and describe the central values of a data set. Next, we're going to explore different distributions, including normal, skewed, and bimodal distributions. And then we're going to examine how data can take on various shapes, depending on the patterns within it. After that, we're going to look at measures of distribution. We're going to focus on concepts like range, standard deviation, and outliers, which describe the spread and variability of data. We're then going to move into probability. Here we're going to discuss concepts like independence, mutual exclusivity, and exhaustiveness. And these are all crucial for understanding the likelihood of different events. Following that, we're going to discuss statistical testing. We're going to focus on how to conduct hypothesis testing and interpret confidence intervals to evaluate the reliability of data. Then we're going to cover charts, graphs, and tables before we finally examine how to apply data. Here we're going to have an emphasis on distinguishing between correlation and causation. And this is a fundamental skill for interpreting research findings. With this introduction, let's go ahead and get started with Objective 1, which focuses on measures of central tendency. These measures provide a single value that represents the middle or central point of a data set, and that helps us summarize and describe the data effectively. The three main measures of central tendency are mean, median, and mode, and each one offers a different way of identifying the center of the data. Let's break them down. First, we have the mean, often called the average. The mean is calculated by summing up all of the values in the data set and then dividing them by the total number of values. So for example, let's say we have a data set with the following numbers: 7, 3, 4, 1, 7, 6. To find the mean, we're going to have to add all of these numbers together. When we do that, we get 28. And then we're going to divide 28 by the number of values. Here we have 1, 2, 3, 4, 5, 6 values. So we have 28 divided by 6. This gets us 4.67. So the mean for this data set is 4.67. Now the mean equally weighs all of the values in the data set, but because of this, it's sensitive to outliers, which can significantly skew the results. For instance, if one of the values in this data set was replaced with 100, then the mean would increase dramatically, even though most of the data points remain relatively small. Next is the median. This is the value that lies in the middle of a data set when the values are arranged in ascending order. Here we're going to consider two scenarios: when we have a data set with an even number of values and a data set when we have an odd number of values. So let's consider the same data set that we just calculated the mean for, and let's arrange the numbers in ascending order. In this case, we get 1, 3, 4, 6, 7, 7. When we attempt to find the median, and we can do that by eliminating the same number of values on both sides, we end up with two values right in the middle. Now, to find the median, we're going to have to take the average of the two middle numbers. So this is going to be 4 plus 6 divided by 2. So this is 10 divided by 2, which gets us 5. So the median for this data set is 5. This is how we approach a data set that contains an even number of values. What about a data set that has an odd number of values? Let's consider the following data set: 1, 2, 3, 4, 5, 6, 7. Let's find the median for this data set. To do that, we're going to eliminate the same number of values on both sides until we get to the middle, and we figure out that our median is 4. So for this data set, it was really easy to recognize one value right in the middle of a data set. Now, the median is generally less affected by outliers, and it makes it a better measure of central tendency for skewed data. Finally, we have the mode. This is the data point that appears most frequently. So once again, in the same data set we saw when we calculated the mean and the median, 7, 3, 4, 1, 7, 6, do we see any numbers that appear more than once? And the answer here is yes. The number 7 appears twice, so that means it is the mode for this data set. Now, unlike the mean and median, a data set can actually have more than one mode if multiple values occur with the same highest frequency. So if we had a data set that looked like this: 7, 3, 3, 1, 7, 6, we notice that 7 appears twice, but so does 3. So it actually has two modes, 7 and 3. So this data set is bimodal. Now, if no values repeat, then the data set is considered to have no mode. In short, each measure of central tendency has its strengths, and it's suited for different types of data. The mean is really ideal for normally distributed data without outliers, while the median is more robust for skewed distributions or data with extreme values. The mode, very useful for categorical data like survey responses, where identifying the most common category is often the goal. Keeping that in mind, let's tackle the following practice problem. This problem says the following data were collected on the ages of attendees at Ray's birthday party: 23, 22, 25, 22, 22, 24, 36, and 20. What is the mean age of the attendees? Is this an appropriate measure for this data? Also, find the median. Let's start with figuring out the median. In order to do that, we want to arrange the numbers in ascending order. We also recognize that there are 8 values in this data set. So that means our median is going to have 2 numbers that we will need to find the mean of to get the median. So here, if we eliminate the same number of values on both sides, we end up with 22 and 23 right in the middle. Now we're going to have to find the mean of these 2 values to get the median. 22 plus 23 divided by 2 gets us the mean of these 2 values. This is going to be equal to 22.5. 22.5 is the median for this data set. Next, we want to go ahead and calculate the mean. The mean is calculated as the sum of all of these values divided by the number of values in this data set. The sum of all of these values is equal to 194, and we have 8 values in the data set. 194 divided by 8 is equal to 24.25. Now the question asks us, is this an appropriate measure for this data? Let's think about this. The mean, it's relatively close to most of the values that are collected for this data set. So it may seem appropriate. But there is the presence of an outlier, that's this 36 value, and the fact that the mean is greater than all but two of the values collected really indicates that the mean has been shifted towards the high end of the range. Looking at the median, however, the median is unaffected by the outlier and it lies close to most of the values in the data set. So we can say that the median is actually a better measure of the central tendency for this data set than the mean. And with that, we've solved this problem, and we can go ahead and move into the second objective titled distributions. A distribution describes how data points are spread out or arranged, and its shape can reveal important characteristics about the data set. Distributions can be classified based on measures of central tendency and measures of variability. Now let's explore the key types of distributions we need to know for the MCAT. Those are normal, skewed, and bimodal. First, we have normal distribution. This is one of the most common and important distributions in statistics. The normal distribution is symmetrical and bell-shaped with the highest point at the center. In a perfectly normal distribution, the mean, median, and mode are all equal and located at the center. This shape reflects that most data points cluster around the average, with fewer data points as you move further away from the average. Now, one key property of the normal distribution is the 68, 95, 99.7 rule, which tells us how data is distributed within standard deviations from the mean. 68% of the data falls within one standard deviation of the mean. 95% of the data falls within two standard deviations of the mean, and then 99.7% of the data falls within three standard deviations of the mean. Now let's use an example to make this more clear. Let's say that the average adult height in the US is 68 inches. And also let's say that the standard deviation is 3 inches. According to the rule that we just discussed, 68% of adults would have heights between 65 and 71 inches. 95% of adults would fall between 62 and 74 inches, and 99.7% of adults would fall between 59 and 77 inches. So this property makes the normal distribution very useful in predicting properties and also understanding variability. So for example, if someone's height is 74 inches, we know that they are within two standard deviations above the mean and therefore taller than approximately 95% of adults. Now let's discuss skewed distributions. This is where the data is not symmetrically distributed. In skewed distributions, the mean, median, and mode differ, and the direction of the skew is determined by the tail of the distribution. Now, there are two types of skew distributions. We have negative skew, also called left skewed. In a negatively skewed distribution, the tail extends to the left. This means that the majority of the data points are clustered in the higher end of the scale, and the mean is pulled to the left of the median and mode. So again, we know that the mean is more susceptible to outliers than the median, so the mean of a negatively skewed distribution will be lower than the median. Then we also have positive skew, sometimes called right skewed. In a positively skewed distribution, the tail extends to the right. This indicates that most data points are on the lower end, while a few extreme values pull the mean to the right. So here, the mean of a positively skewed distribution will actually be higher than the median. Finally, we have bimodal distributions. This is characterized by two distinct peaks separated by a valley. And it's important to note that a bimodal distribution might technically have only one mode if one peak is slightly higher than the other. However, even when the peaks differ in height, the distribution is still referred to as bimodal. Now, if there is sufficient separation between the two peaks, or if the amount of data between them is relatively small, the bimodal distribution can be analyzed as two distinct distributions, though this is not always necessary, but it's important to keep in mind that it's possible. For example, if you measured the heights of all adults, maybe the distribution might show two peaks, one corresponding to females and one corresponding to males. And recognizing bimodal distributions is important because they often indicate or could indicate some underlying differences in the data that may warrant separate analysis. With that, we've completed Objective 2, and now we can move into Objective 3, where we're going to explore measures of distribution. These measures describe the spread or variability of data and help us understand how individual data points relate to the overall data set. The main concepts that we're going to cover in this objective are range, interquartile range, standard deviation, and outliers. Let's first start with range. This is the simplest measure of distribution, and it's calculated as the difference between the largest value and the smallest value in a data set. So let's say that we have this data set with the following numbers: 3, 7, 10, and 15. 15 is the largest value, and 3 is the smallest value. So our range is going to be 15 minus 3, and that's equal to 12. Now, while the range provides a quick way to gauge the spread of data, it's important to note that it is highly sensitive to outliers. Next, we have interquartile range. This measures the spread of the middle 50% of the data. Interquartile range is related to the median and to the first and third quartiles. Quartiles divide data, when placed in ascending order, into groups that comprise 1/4 of the entire set. Now, there's some debate over the most appropriate way to calculate quartiles, but for the purpose of the MCAT, we're just going to use the most common method. This method has 4 main steps. The first step says to calculate the position of the first quartile, Q1, in a set of data sorted in ascending order, multiply n by 1/4. N refers to the total number of data points in the data set. Step 2 says, if this is a whole number, the quartile is the mean of the value at this position and the next highest position. Step 3 says, if this is a decimal, round up to the next whole number and then take that as the quartile position. And then the final step says to calculate the position of the third quartile, Q3, multiply the value of n by 3/4. Again, if this is a whole number, take the mean of this position and the next. And if this is a decimal, round up to the next whole number and then take that as the quartile position. The interquartile range is then calculated by subtracting the value of the first quartile from the value of the third quartile. So interquartile range is equal to Q3 minus Q1. The interquartile range can be used to determine outliers as well. Any value that falls more than 1.5 interquartile ranges below Q1 or above Q3 is considered an outlier. Now, this is best understood by doing a practice problem. So let's tackle this one. This one says, using the interquartile range, Determine whether the 36-year-old from Ray's party is an outlier. The ages are provided in numerical order below for convenience. In order to determine whether this point is an outlier, we first need to calculate the interquartile range. To do so, we have to determine the first and third quartiles, which I'm going to refer to as Q1 and Q3 respectively from here on out. Now, this data set, it contains 8 values, and this number is going to be really important to us when we calculate Q1 and Q3. To calculate Q1, we multiply 8 by 1 over 4, and this gets us a value of 2. So this means that Q1 is going to be the mean of the second and the third values in this ordered data set. This will be 22 plus 22 divided by 2. This gets us 22. This is our value for Q1. For Q3, we're going to take 8 and we're going to multiply it by 3 over 4. This gets us a value of 6. So Q3 is going to be the mean of the 6th and the 7th values in this ordered data set. 24 plus 25 divided by 2, this gets us 24.5. This is our Q3. Then to get the interquartile range, we will have Q3 minus Q1. So 24.5 minus 22. And this gets us a value of 2.5. Now, outliers are data values more than 1.5 interquartile ranges below Q1 or above Q3. So we're going to take this value 2.5, we're going to multiply it by 1.5, and this gets us a value of 3.75. We're going to take 3.75, we're going to subtract it from Q1, and that gets us a value of 18.25. Then similarly, we're going to take 3.75, but we're going to add it to Q3. This gets us a value of 28.25. This means that any value above 28.25 or below 18.25 will be an outlier. Since 36 is well above 28.25, it is indeed considered an outlier in this data set. And with that, we've completed this problem. And now we can move into our discussion on standard deviation. Standard deviation is a widely used measure of variability, and it quantifies how spread out the data points are around the mean. Standard deviation is calculated by taking the difference between each data point and the mean, squaring this value, and then dividing the sum of all of these squared values by the number of points in the data set minus 1, and then taking the square root of the result. This is mathematically expressed in this form where xi represents each data point, x bar represents the mean of the data set, and n is the number of data points. Standard deviation is particularly important because it relates directly to the normal distribution. Recall that 68% of data in a normal distribution falls within 1 standard deviation of the mean, 95% within 2, and 99% within 3. Now we're going to jump into a practice problem to help us understand how to calculate standard deviation, but first I want to revisit the topic of outliers. Outliers, these are data points that deviate significantly from the rest of the data set. Outliers can arise due to true population variability, due to measurement errors, or due to the presence of a non-normal distribution. Outliers are important because they can distort measures like the mean and range, and that can sometimes lead to misleading conclusions. Now, it is then useful to know how to approach data with outliers. Outliers typically result from one of 3 cases. The first case is a true statistical anomaly. For example, someone who is over 7 feet tall. That is a true statistical anomaly. The second cause is a measurement error. For example, reading the centimeter side of a tape measure instead of the inch side. And then the third cause is a distribution that is not approximated by the normal distribution. For example, a skewed distribution with a long tail. However, something that's important to note, not all outliers should be removed automatically. Instead, researchers have to determine whether an outlier represents a legitimate data point or a measurement error before deciding how to handle it. If there is a measurement error, then the data point should be excluded from the analysis. However, the other two situations are a little bit less clear. With that, let's jump into that practice problem. This one says, calculate the standard deviation for the following data set. We have 5 numbers, 1, 2, 3, 9, and 10. Our first step is to determine the value of the mean. So that means we're going to sum up all of these values, 1 plus 2 plus 3 plus 9 plus 8, and then divide by the number of values we have in the data set, which is 5. The sum is going to give us 25, and 25 divided by 5 is equal to 5. So this is our mean for the data set. The next step is to find the difference between each data point and the mean, and then square this value. So here in the data set, I've done that for all 5 values. We have our first value in our data set, that's 1. 1 minus 5 is equal to negative 4, and then we want to square that value. Negative 4 squared gets us 16. Then we're going to do the same for 2. 2 minus 5 is equal to negative 3. Negative 3 squared is 9. Then we have our third value, 3. 3 minus 5 is equal to negative 2. Negative 2 squared gets us 4. Then for 9, 9 minus 5 is equal to 4. 4 squared is 16. And then finally, we have our value 10. 10 minus 5 is equal to 5. And 5 squared is equal to 25. Then we're going to take all of these values in our third column, and we're going to sum those up and then divide by the number of values minus 1. And then all of that, we're going to take the square root of it. So here we're going to do 16 plus 9 plus 4 plus 16 plus 25. And then we're going to divide that by 5, the number of values in this data set minus 1. And then we're going to take the square root of all that. Now the sum here, this numerator is going to be 70, and 5 minus 1 is equal to 4. So we're going to be taking the square root of 70 over 4, which should be approximately 4.18. And with that, we've solved this problem, and now we know how to calculate standard deviations. And we're going to go ahead and end the video here. In the next part, we're going to start objective 4 and talk about probability. Please let me know if you have any questions, comments, concerns down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day, future doctors.